Hey, welcome back everyone. So in chapter 7, we'll introduce the topic of sampling distributions, but as always, let's first review the learning outcomes of the chapter. So in this video, we will discuss the concept of sampling error and learn what it represents. Then in the next two videos, we'll learn about the sampling distribution of a sample mean and a sample proportion, as well as review why the central limit theorem is so important. So let's get started. So we only have one topic in this video, which is sampling error. So let's jump into that now. Now recall in chapter 1, we learned the difference between a population and a sample and how they relate to each other. So a population is an entire group that we're interested in studying or understanding, and then a sample is a subset or a smaller group that's selected from the population. So the sample error is the difference between a measure computed from a sample, known as a statistic, and then the corresponding measure computed from the population, which is known as a parameter. So here we have our formula for our sampling error, where we take the sample mean minus the population mean. So some things to note about the sampling error is that we'll be using simple random samples. So recall, this is where we selected a sample from the population, and every sample has the same chance of being chosen. Now, the size of the sampling error depends on which sample is selected. Since it is random, there could be a mix of numbers, or it could be skewed to smaller or larger numbers. So these different samples will determine the size of the error. Now, the sampling error can be positive or negative. And then finally, there's a chance that you could get a different sample mean for each sample. So imagine, as an example, where I used our class as the population, and I wanted to select a random sample of 5 students. I can repeatedly select samples of 5 students and calculate the sample mean for those students, such as things like your height or how long it takes you to drive to work. And then for each of these samples, I could get a different sample mean each time. So let's go ahead and check out a simple example. Now, recall in chapter 3, we learned how to calculate the population mean and the sample mean. So this is more of a refresher, where we'll add up all of our x values and then divide it by the population size, or in the case of the sample mean, the sample size. Here in the example, the population mean is denoted by mu, and it equals to 32.5 minutes to commute to work. So then we take a sample of 6 drivers, and that yields us a sample mean of 36.2 minutes to get to work. Then for our sampling error, we'll take the sample mean minus the population mean, or 36.2 minus 32.5, and we get a sampling error of 3.7 minutes. So in other words, we are acknowledging that our sample is not a perfect representation of the population because we are not studying the entire group. We are just studying a subset. So we must recognize that there's going to be a slight difference between the sample and the population data. So let's go ahead and take a look at another practice problem. So here's problem 7-6. So the following data are 16 values in a population. So in A, we're asked to compute the population mean. Then in B, we're asked to compute the sample mean based on a simple random sample of 9 numbers, and then calculate the sampling error. So let's start with A. Here is the mu symbol again for the population mean, and the formula is going to be the sum of all of the x values and then divided by the population, or big N. So in the numerator, if we add up all the numbers, we get 288. The population size is given to us at 16. Then we take 288 and divide by 16, and we get 18 for the population mean. So the calculation for the sample mean is the same as the population mean, except we'll now divide by the sample size. So in the numerator, if we add up all of the numbers in the sample, we get 153. Then the sample size of 9 was given in the problem. So 153 divided by 9 gets us a sample mean of 17. So now here is the formula for the sampling error again. So it's really important that you get the order correct here. So the sample mean will always be first, and then we subtract the population mean. So we take 17 minus 18, and we get a -1. So now imagine if I go back and I select a different sample, and it's some different combination of 9 numbers, and I run it again, I'll likely get a different sample mean, and in turn, a different sampling error. So now in part C, you're asked to determine the range of extreme sampling error for a sample size of 4. The idea or the concept behind the range of extreme sampling errors is what would our lowest possible sampling error be if we happen to get all of the lowest numbers, or the highest possible sampling error if we happen to get all of the highest numbers. So I've taken the 16 numbers from the prior slide, but now I've ordered them from lowest to highest. So the 4 lowest and highest numbers are now highlighted in blue. So if the samples selected are these 4 numbers here, 12, 13, 14, and 15, for the lowest possible, then we would calculate our sample mean by adding up the numbers in the numerator, and we get 54. So then we divide by the sample size of 4, and we get a sample mean of 13.5. Next, we're going to calculate our sampling error. So I'll take the sample mean of 13.5 minus the population mean of 18 that we calculated before, and we get a negative 4.5. So now we'll repeat this exercise for the highest possible numbers in the sample. So we're going to add up these numbers here, the 22, 23, 23 again, and 25, and we get 93. So we divide by the sample size of 4 again, and we get a sample mean of 23.25. We'll now calculate the sample error for this sample mean. So we'll take the sample mean of 23.25 and subtract 18, and we get 5.25. So the range of extreme sampling error for the sample size of 4 is from negative 4.5 to 5.25. Well, everyone, that wraps up this video on sampling error. So in our next video, we'll learn about the sampling distribution of the mean.